To continue with our topic 4, we now discuss the general second order system. We have just discussed the 4 classifications, no, or the special cases of the second order system. This time, let us now focus on the general second order system. So the natural frequency with this symbol and the damping ratio with this symbol are two quantities that can be used to describe the characteristic of the second order transient response. Just as the time constant describe the first order system response. So once more, kung sa second order, we talk about natural frequency and damping ratio. For the first order, we're talking about time constants. Recall again that the general equation is given by this, no? So we have here constant B that is equal to the constant of the last term, no, of the trinomial, and an a constant value or coefficient of the second term. This general second order equation is actually equivalent to this equation in terms of the natural frequency and the damping ratio, meaning to say that B is equals to the quantity, the square of the natural frequency, and the A is actually equal to twice the product of the damping ratio and the natural frequency. Let's talk about the natural frequency. The natural frequency of the second order system is the frequency of oscillation of the system without damping. For example, the frequency of oscillation of a series RLC circuit with the resistance shorted, no? RLC ito, but parang tinanggal natin ang resistor, parang pinag-short natin ng ganyan. Then, it would be the natural frequency of the circuit will be oscillating. No? The frequency of oscillation will be its natural frequency of this circuit. From the transfer function, the natural frequency would be known and the damping ratio could be solved as follows. No? As I've mentioned earlier, okay, that natural frequency will be equals to the square root of B. And from there, knowing the natural frequency, then, by the way, the damping ratio is defined to be equal to the exponential decay frequency over the natural frequency. Or that is equals to 1 over 2 pi of the natural period over the exponential time constant. So once more, this damping ratio could be written as this, no? The absolute value of this, okay? And over the natural frequency, or A over 2 over the natural frequency. So if the damping ratio is known, then the parameter A could be identified. No? If this is given, then we could solve for A. So to illustrate, this is the so-called exponential decay generated by the real part of complex pole pair. And this is the sinusoidal oscillation. No? This is the output response, itong curve na ito. And it is damping out. Nagda-dump out siya. The oscillation is being dumped. Okay? Now, this table gives us the step response in terms of the damping ratio. So, if the damping ratio is 0, then we could expect an undamped response. If the damping ratio is from between 0 to 1, then we could expect that the step response would be underdamped. If damping ratio is equals to 1, then the step response output could be critically damped. And if the damping ratio is greater than 1, it could be over damped. Peak time. So peak time is given by this formula, and again, we only need to know the natural frequency and the damping ratio to solve it. And we have a so-called percent overshoot. Again, it's a function of the damping ratio. Yeah. There is another formula. If the damping ratio is given, or rather, if the percent overshoot is given, okay, then we could solve for the damping ratio. The settling time is given by this 4 over the product of damping ratio and natural frequency. And the rise time is given by this relationship between the damping ratio and the rise time. In this case, our rise time is normalized by 10. No, it's meaning normalized or multiplied by 10. No, so we could get a whole numbers. No, for graphing or representation purposes. So for our example, given this transfer function, let's determine the response characteristics of this transfer function system. Okay, so once more, this is our transfer function. So given the transfer function, solve the following. The natural frequency. So since we have 100 here, square root of 100 is 10. So we have here 10. Okay, so again, this is the formula, no, general formula of our second order. Next is the damping ratio. So damping ratio is equals to 2, damping ratio, natural frequency equal to 15. So 15 divided by 2 is, or rather, since we know already that natural frequency is 10, 10 times 2 is 20, so damping ratio is equal to 15 over 20, or that is 3/4, or that is 75%. The peak time could be solved to be 0.75. Of course, from this value, you simply substitute the 10 here and the 0.75 here. You will get 0.475. For the percent overshoot, we simply substitute that to this equation, okay, and get 2.837. And for the settling time, it will give us TS equal to 0.533 with this formula. And for the rise time, okay, it will give us 2.2965 if we will base it from this table. No, since we have the damping ratio is 0.75, so it's between 0.7 and 0.8. If you're going to get the average of these two, you will exactly get 2.2965. Now, if we're going to put this transfer function in MATLAB, it will give us this response characteristic. So let's compare. Now, the rise time, it's 2290. It's 2.2965. Again, this is normalized. So if you divide it by 10, they will be close enough. For the settling time, okay, 0.533, and this, so they are almost equal. Okay, and for the curve, this is the step response. And again, the end. Thank you so much. Okay, so it's a somewhat under-damped system. Kindly view the following videos for additional information. Thank you.